Hello and welcome back to another video. In this video, we will move on to chapter 3, which is all about techniques of integration. So we've learned some techniques so far, right? So far in our integration toolbox, we have 1, the antiderivative formulas. 2, we have U substitution. And 3, we have using areas or Riemann sums, which was the original way we learned with rectangles and other shapes. So section 3.1 is going to add integration by parts to our integration toolbox. And this is a technique based on the product rule for derivatives. So integration by parts is sort of like a product rule. So integration by parts is a sort of product rule for integration, right? Or for integrals, right? So let's say, for example, right, we can integrate, right? If we were given x times sine of x squared, right, we can use this, right? We can solve this using U substitution, right, where we let U be x squared and then du be 2x dx, which then we multiply by a half in order to get x dx, right? But if we were given instead x times sine of x dx, right, it doesn't work as nicely because if we can't just let U be x, right, because then that would mean du is just 1 dx or dx, and that would mean we would just change the integral, right, to be in terms of U, but we didn't simplify the integral anymore. It's literally the same exact integral, just using a different letter for our variable. And so this is when integration by parts will become in handy when we have a product of two things like this. So what is integration by parts? Let's write it out. So integration by parts. So we're still going to be using U's and stuff like that, but it's going to mean a little different. So we're going to let U be some function f of x and v be some other function g of x. Right, so those are both functions. Then the integration by parts formula for the integral is the integral of u times dv is equals to uv minus integral of v du. So right, basically we're gonna choose a u and then let everything else be dv, right? And then we have, right, du is just the derivative of whatever we set u to, and then v is the antiderivative of dv. Okay, so let's do an example, right? So basically what we're saying is this is how we're seeing our integrals when we're doing integration by parts. It has to be set up this way, and then we're going to solve it by plugging into this right hand side. So we're going to plug in u, plug in v, and plug in dv, and then solve. Right, so let's do an example. Oops, back to black. Example. So use integration by parts with u equals x and dv equals sine x dx to evaluate the integral of x times sine x dx. So the one we couldn't do earlier, right? So we're letting u be x. So then the derivative of u, right, the derivative of just x is 1 dx, right, which is just du is dx. And then we're also letting dv be sine of x dx. So then v is the integral of dv, right? So we literally have to integrate sine x of dx, which you should have on your antiderivative formula. So remember, the antiderivative of sine is negative cosine. So that's what v was equal to. So when we have our formula for integration by parts is u dv is equals to uv minus the integral of v du, right? So u is just x, so we have to plug that in there. So this is equals to x, and then v we said was negative cosine of x, so we'll plug that in here, right, for v right here. And then we're going to have to plug it into this v as well, so it's going to be minus the integral of negative cosine x, and then du is dx. So we'll just replace this with dx. Right, so if we simplify, right, this just becomes negative x times cosine of x. If we pull out this negative sign, this will become a plus sign, and then we have to integrate cosine x. So look at your antiderivative formula if you don't remember that the antiderivative of cosine is just sine, because the derivative of sine is just cosine. Okay, so this is the integral of x sine x dx. And that is it for integration by parts. So it's pretty much the challenge is choosing a correct u and dv. So let's say they didn't tell you what to set to u and what to set to dv, right? How to know what to choose for u and dv. How in the world will we know? So sometimes it's a matter of trial and error, but the acronym LIATE can help us make better educated guesses. So what does it stand for? L-I-A-T and E. So L is logarithmic functions. I is inverse trig functions. A is algebraic functions. T is trigonometric functions. And E is exponential functions. So basically, the type of function, so the type of function that appears first in the LIATE list should be our first choice of u, right? So if there's an ln function, then you should choose that. If there is an inverse trig function, right, which we either denote as arc cosine, arc sine, or we use the -1. Algebraic functions, which are like x, x squared, 2x, so on and so forth. Trig functions, which are like the regular sine, cosine, tan, secant, etc. And exponential functions, which are like e to the x, 3 to the x, and so on. Right, so you want to go down this list. And the first one that qualifies is what you make u. So then when we have chosen u, dv is set to be the remaining part of the integral. Of the integrand, right? Sorry, the function that's being integrated. So let's do another example where now we have to choose u. So the problem given to us is evaluate the integral of ln of x over x cubed dx. So the first thing you have to notice is that this is equal to 1 over x cubed times ln of x dx, right? And we can rewrite, remember, we always want to bring any powers in the denominator if we can to the numerator by making the exponent negative. And then this is the function we're working with. So what should we make u? Well, off the bat, we hit L because we have a log. So we're going to let u be ln of x, and then dv is everything else. So the x to the -3rd, and then the dx as well. So then when we take the derivative of u, we get 1 over x dx. And then when we do the integral of dv, we get v, which, remember, we have to add 1 to the power and divide by the new power. So we plug this all into the integration by parts formula, which, remember, is uv minus the integral of v du. So then u, we said, is ln of x, and dv, we said, was x to the negative, I don't want dv, right, I want v. So v is x to the -2 over 2, and then v, right, is x to the -2 over -2, and du is 1 over x dx. Okay, so now let's simplify this stuff, right? So what I can do, this should be negative. What I can do is put out the -1/2, and then I'll have times x to the -2 times ln of x. And then if I take out the -1/2 from here, I'm left with the x to the -2 times 1 over x dx. Right, and remember that x to the -2 is just 1 over x squared, so we can implement that. So this becomes -1 over 2x squared times ln of x plus 1/2. And then this is 1 over x squared times 1 over x, which, right, that simplifies to, right, let's bring everything else down, and then that simplifies if we multiply across 1 over x cubed, which we know 1 over x cubed we could change to be, right, x to the negative, don't know what happened there, x to the -3, and then we can actually integrate that. So this is -1 over 2x squared ln of x plus 1/2, and then we add 1 to the exponent and divide by the new exponent. We need our plus c since we don't have bounds, and this is -1 over 2x squared ln of x minus x to the -2 over 4 plus c. And then we can bring the x to the -2 down as well. So this is 1 over 2x squared ln of x minus 1 over 4x squared plus c. And that is the final answer.